So hi everyone, welcome to the third talk of the seminar series on security and privacy in machine learning. Today we are super excited to have our guest speaker, Professor Ben Zhao from UChicago. He'll be discussing his super recent work, I believe, on adversarial robustness and forensics in deep neural networks. Short bio about our guest speaker. He's a professor at professor of computer science at University of Chicago. Before UChicago, he held the position of again in like professor of computer science at UC Barbara. Completed PhD from Berkeley and BS from Yale. I think there's a very long list of awards, but to summarize, Professor Zhao has received NSF Career Award, MIT Technology Review, TR35 Award, and many others. And I think we have like, I think most of us have at some point read like some even like news article covered in like the major outlets about the cool work. And yeah, like again, he has worked like very extensive and extensively in the areas of security and privacy. And yeah, looking forward to hearing more about your recent work. I think the virtual stage is all yours. Yeah.
Great, thank you, Akash. Really happy to be here. Thank you all for joining. So yeah, I guess today I'm going to talk a little bit more about some of the recent thoughts that I've had and perspectives my students and I have had on researching sort of adversarial robustness for deep learning systems and deep neural networks. Yeah, so let's get into it. Let me just start. Yeah, so the obvious preamble on sort of adversarial machine learning, you know, it's got to be here, but I don't need to say it. We all know about deep learning. We all know about how powerful it is. We all know how many broad applications there are in different contexts, but we also know about all the different types of attacks that are already proven to be very much pervasive in terms of vulnerabilities for these deep learning systems. So obviously adversarial examples and poisoning attacks and you know, privacy-based attacks like model extraction, inversion, and so on. So there's a whole, you know, research line of work for several years now. I think, you know, started back in the early 2013, 14-ish, right? And it's been almost a decade. And it's really sort of broadened out to be multiple research areas, multiple different research communities. There's sort of the more security and privacy community, so Oakland, CCS, Usenix. There's the more core ML community, you know, ICM NeurIPS, iClear, CVPR, and then even other specific application domains that have their own versions of adversarial machine learning problems and challenges and so on. So I want to talk primarily today about adversarial robustness, so focus on active and adaptive attackers, not necessarily sort of benign natural robustness issues, but you know, really adversarial circumstances. So you know, my lab's done a whole bunch of work in this sort of general space, I guess, and so there's just a smatter of some of the different categories, obviously on adversarial perturbations and defenses, attacks and defenses back and forth, on poison backdoors and so on, and then also in the sort of the broader spaces of weaponized machine learning attacks, and also you know, defending privacy against invasive ML. So today, I guess I'm primarily I'm gonna try to sort of motivate some of the perspectives that we have in recent years with just a brief mention of a really quick fly through a couple of the papers that were older that shaped our thinking about the space. Recently, I should say, recent old papers. And then I'll talk primarily about the digital forensics work, which is coming up at Usenix Security in August, I believe. Okay, so getting into it, you know, adversarial examples on neural networks are very much a thing. They've been around since 2014, I think, was one of the early papers by Goodfellow et al. And this is the standard obligatory figure, right? So you have a stop sign, it gets classified, add some tiny little adversarial noise to it, and all of a sudden it becomes some misclassified input. And that's sort of the canonical example of this. And I want to start today by talking about, some experiences we've had with a couple of recent papers that have shaped and sort of pushed me and my group to move in slightly different directions. All right, so one of the things to very briefly, again, this is all old hat to many of you, I'm sure, just looking at the progression of attacks that have sort of matured and really gotten much more powerful over the years, right? They all based on some generic optimization search for some small delta that is difficult to see with the human eye, and yet sufficient to push an input across some classification boundary in the model that right? But what is interesting is just how these sort of attacks and defenses have progressed. And what's been clear, what's been reasonably evident is that over the last few years, defined by like 7, 8-ish, right? This maturity, this community has matured quite a bit, and it's been a particular pattern where, interesting defenses get proposed at many different places, and almost very quickly, usually within a year, within 12 months, some adaptive attack is proposed. Some specific, some more general that categorically or significantly destroys really some of these defenses. And this has been happening over and over again. And some of the more recent papers have been, attacking entire sets of defenses and invalidating them. So, at a very high level, one can step back and say, boy, we haven't really done great with defenses. Outside of sort of adversarial training, which certainly is promising, but really has its own caveats with respect to not only training costs, but also in terms of the price that you pay for drops in benign accuracy. Outside of adversarial training, there's really no sort of single known effective defense that has been robust against countermeasures, against adaptive attacks that have come later. And this is, a little bit discouraging. And, in a way, we've really sort of gotten into this cat and mouse cycle of defenses occasionally being proposed, lots of attacks being proposed in the meantime, but then defenses being defeated fairly quickly by adaptive attacks, right? And so I want to briefly illustrate this point by talking a little bit more about one of our own papers in the space. This was like a year and a half ago-ish at CCS 2020, because it really cemented, it really sort of concretized just how real this cat and mouse game was, and it sort of drove some of the later thinking that we had in the space. So this was a paper we just called Trapdoors paper at CCS 2020. And it's very simple. The perspective that we took on this paper was basically that, if you look at existing defenses, there are lots of defenses, and you could think of them as falling into two big buckets. Some of them basically looked at this question of adversarial perturbations and said, well, we're going to try to patch them. We're going to try to find potential adversarial perturbations and remove them by either smoothing out the space or training against it. There are other techniques, the other bucket, meaning we could try to hide them, make these natural sort of perturbations or indentations in the space, if you will, where training hasn't been great, and make them very difficult to find. And so, obfuscate them, effectively speaking. And so what we wanted to do at the time with the Trapdoor paper was we wanted something a little bit different that was neither of these two things. And so, both of these approaches have been shown to be fairly limited. You can't patch all the perturbations without paying a really high cost. And obfuscation, has been shown time and time again to be limiting, because you can always find workarounds to be more effective at finding these perturbations. And there's just so many of them that obfuscating all of them is really difficult. So our approach at the time was basically to say, we'll do the opposite. We'll do like a trapdoor. We'll do a honeypot type of approach. Okay, and the honeypot version of this will be to say basically, this is like the best I could do in terms of finding illustration for this. Imagine like a surface, a classification surface that is already indented, and there's little holes here and there, indentations or whatever. And what we're effectively doing is we're taking a hammer and smacking it intentionally ourselves as a defender. Okay, and we're going to create an indentation or an adversarial example. So not necessarily big in some, in a loss sense, but in a more pervasive sense in that it impacts the entire classification space, and it's hard to ignore. And so the idea then is that the defender basically artificially injects a vulnerability into their own model during model training in a very controlled way, such that it becomes very obvious or is difficult to ignore when you're trying to apply a optimization method to this model. So an attacker using any sort of optimization model, optimization method, SGSM, all the way to the best and the latest and greatest, most efficient projected gradient descents and different versions of gradient descents, will easily find this sort of vulnerability, right? And the better that these optimization methods get, the faster they find what it is that we put in. Okay, and that's great. And so what happens then is the attacker says, okay, I found this great vulnerability and it's very subtle and I can inject a very small delta, but it's the delta that we know, right? The defender knows. And so when the attacker comes in and they add that sort of delta to their input, we can actually at inference time look for any sort of inputs that have this particular signature that looks like the injection that looks like the vulnerability that we injected. Okay, so this is sort of a combo defense, right? You modify the training, but then you look at inference time and you can reliably detect defenders, attackers. Okay, so how do we do this? The simple answer is that this is effectively a backdoor poisoning attack, but you're the defender and you're intentionally creating a backdoor that is optimized for the classes that you're trying to protect. Okay, so again, my point is here is not to go into the details of this paper. My point is to talk about the experiences after the paper. So let me skip past some of this stuff. But basically, the idea is to inject a optimal solution for some optimization function that the attacker is looking for when they're trying to create an attack. Okay, so yet another sort of visualization version of mental picture of what this might look like. Oh no, my office light is. So hold on one second. My office light keeps on turning itself off because it's trying to save power, and things not moving. Therefore, I don't exist. Okay, so this mental image then is just an issue of like, okay, here are these natural perturbations. We take a big hammer and we smack our own classification manifold to create a big indentation so that there's some, local minimum that is even better than the usual, and an optimization function will find it. Okay, all right. So this worked really well at the time. We did all these tests and look at all these different attacks and all these different tasks and different task models, and everything is really, really strong. It's great. Also, false positive rate is really quite low because you just don't accidentally bump into this very specific vulnerability that you put in using benign inputs. So it's great. And the nice thing about this is that because it is so focused, it doesn't actually have any impact on model accuracy, benign classification wise. So sort of all the checkboxes that you want from a nice defense. All right. And then of course, because we're submitting to a security conference, there's a huge emphasis on sort of countermeasures and trying to make these things robust, right? So we do all sorts of things. We try things like, well, what if you can identify things that are related to this particular mechanism and prune out the neurons? What if you can try to learn the model, make a copy of it basically by training a surrogate version of this model that hopefully leaves the trapdoor behind. We try to look for existing natural perturbations by using really small learning rates and more adaptive attacks. All these different things we tried and they all fail for one reason or another. Most of it's because this trapdoor is so integrated in with the model that it turns out to remove it or to disrupt it, you actually do more damage to natural classification before you can actually remove the trapdoor. which is really nice, and that's what you want. So this is all the internal sort of quote unquote countermeasure that we did, right? So we'll finally get this paper, and this is CCS 2020, and the paper gets in, and lo and behold, this is before the camera ready version, right? And I'm sure many of you know Dr. Nicholas Carlini, and Nicholas is great. He is like a sort of a really singular talent in terms of creating great attacks in the space. So after he heard about the paper, he's like, oh, this is super interesting. He reaches out, says, can I play with the source code? We're like, of course, here's the source code. Overnight, literally overnight, he comes back and says, okay, I broke it. And I'm like, oh, crap. That's bad, obviously. So we check it, and it seems like, okay, so it's not quite as bad as we thought, because Nicholas made use of total knowledge of the system, including some runtime randomization parameters that we used. And we're like, okay, well, that's, sort of strictly speaking, really white box, but, I think in a realistic setting, you don't have that parameter. And so we say, okay, maybe a slightly stricter threat model. And Nicholas is like, okay, fine. After 3 days, he comes back with another attack. And this time it really does work, and doesn't make use of sort of, total knowledge of the space. And so we're like, oh boy. Lucky enough for us, we had a few bullets, left in the chamber, and so we apply some of our other techniques that we hadn't put into the paper yet, additional defense sort of mitigation techniques. And it turns out that using all of them, we could sort of push back on Nicholas's vaulting attack significantly, to where it wasn't embarrassingly bad. It was like, I think 20% attack success rate or something like that. Still not great by any stretch of the imagination. But what it did for us was really like this realization that, holy cow, it is just so difficult to craft truly adaptive countermeasures. And you say this, you see sort of papers come out, and you can think this, and people say this all the time. It's like, oh, you want more powerful countermeasures. But we really, really tried. Like, we spent months on these countermeasures, and yet here's Nicholas, who comes around and within a few days is able to break it in a reasonably meaningful way. Not completely disable it, but at least to the point where it's significantly degraded to where it doesn't look as good as we thought it would. And that was really sort of, shaking in terms of just realizing how challenging it was to do a really good defense. And and even more than that, a year later at the same conference, CCS, a specific paper was written with the exact purpose of breaking our paper. And that's something that I'd never been a part of, which was super interesting. It was like, okay, well, I mean, I guess that's impact, but someone basically said, all right, trapdoors are interesting, we're gonna go break it. And here's an entire paper telling you how to break it. And then also Nicholas took some of his ideas that he had from our paper and others, and there was additional paper that he wrote up in iClear 2022 this year, talking about sort of orthogonal projected gradient descent, another attack method. So what does this teach us? The takeaway was that, this current threat model, this current way of thinking about what is robust is really, really difficult for the defender. And, given these threat models that we're working with, it's just almost impossible to do a really robust defense. That was my takeaway. And we actually had a similar experience in the backdoor space. So that paper in trapdoor space was just talking about adversarial examples, right? Sort of inference time attacks. We had a different experience at CVPR using our paper on backdoors in the physical world. And in this paper, it was different. We were on the other side, and I'm not going to bore you with the details, except to say that, backdoor attacks, there are poison attacks where basically misclassification can be caused at inference time when the attacker uses a specific trigger that they trained into the model, right? So if you can corrupt the training data, you can have students who put on this particular funny pair of sunglasses, and all of a sudden they become me using the facial recognition model. Okay, so that's just backdoor attacks. So yeah, I'll get to the questions a little bit later, right? But what was interesting about this paper was that we were actually the attackers, because we were concerned that all the defenses and literature were really focused on digital triggers, focused on little pixelated things that you could train to the model. But we were more concerned about, or more interested in thinking about, like, physical attacks, Okay, so there's a bunch of defenses, including some of our own work from 2019. But we're curious about how they would stand up to physical triggers, meaning physical objects that were naturally embedded inside the photos themselves, for example. So here you see a few images of a couple of my students wearing sunglasses mislabeled as me, right? So this is not a pixelated square pattern or some sort of image perturbation that's introduced into the pipeline. This is actually inside the image. And basically, the long story short, everything breaks. All the defenses break. And they all break for very reasonable reasons. If you go back, and so we actually dove back in to analyze exactly why every defense breaks. And it turns out they're all making slightly unrealistic assumptions about the triggers themselves. Many of them make assumptions about the trigger's impact, its localization of activations inside the neural model. NeuroCleanse, our own paper from 2019, made too strong assumptions about like how small the triggers were, so it failed on bigger triggers. So they all fail. And again, this is sort of like indicative of what we saw in the adversarial perturbation space, which is that, again, defenses are just really, really hard. And in this case, it wasn't even a countermeasure targeting any specific defense. It was just a natural extension of the attacks of like, if you want this to happen in the real world, okay, we train real world physical triggers objects, real world physical objects as triggers, and all of a sudden, these defenses all break. So that led to sort of a period of thinking, when we're really considering this issue of like, are we just stuck? And having been in the space for a little while, particularly the security and the privacy side of these conferences, and I would look at some of the papers that had been submitted and published, and it seems like we're really in this plateau state where it is reasonably, I want to say easy, it's never easy, but it's reasonably feasible to write and create new attacks. But defenses are just in a really stuck mode. It is very, very difficult to come up with a defense that is reasonably robust and that has some chance of withstanding the test of time. Not even like a long period of time, but just a cycle or two of the publication wheel, right? And it seems like there's always a stronger, more powerful attack. And it seems like that part of this is that there's a built-in asymmetry, is that the attacks tend to be a little bit easier than defenses, in that the expectation and what we want out of the attacks is more of an existence proof style rather than an expectation that's going to work against all defenses, for example. So all that's to say that, we had this period of time when we were discussing things in the lab and just trying to figure out like, is this the right state of things? And if we can try to improve this, what do we do? One take from this is that this type of work is not necessarily helping real world systems in a particularly meaningful way, right? This continued cat and mouse game of more defenses, more attacks that breaks them. How does this help a practitioner who's trying to deploy deep learning systems? And so we pose that question and we think about this issue of like, if you're someone who's really trying to deploy real world models, right? What would you like to see instead? Perhaps these publication cycles of attacks and defenses aren't necessarily super helpful. So one possible interpretation of this is that maybe given the current threat model, we've sort of maybe not quite plateaued out, but we're coming close to saturation of what you can do in this threat model. And perhaps we should step back and really think about whether the threat model can be expanded to be more realistic, to be more productive and useful for real world systems. Okay. So just to crystallize this, right? One view of this is that in the current adversarial machine learning research, we have this one cycle, which is, here's a defense, and against some attacks, it works, great. Against some defenses, some attacks, it fails. And basically the reaction is, okay, well, it's trash. Let's throw it away and start from square one. But that's not how things work in the real world, right? So this is a photo of, sorry to pick on Boston Dynamics, but this is a photo of like one of the robots falling down, okay, in a real world task. And it's kind of funny, but this is how robots learn, okay? And this, in a way, is how the real world security systems work. And I think, we all know this, and perhaps we've just forgotten about it a little bit, right? Defenses in the real world are not perfect. If you have a persistent enough attacker who is sufficiently incentivized, they almost always eventually win, right? And so there's a question of like, in that world, what does this look like? What do you do in that world? And we know from real world examples in network security and operating system security and software security, that is not the end game. That is not the end of the story. Companies don't fold and say, we give up and let's go bankrupt, because our network has been compromised, right? It's not ideal, but there are things that you can do. So in that more realistic setting, you can talk about things like digital forensics. And digital forensics is this general idea that attackers can and often do win, right? So you start from following a successful attack incident, okay? And what you do is you take the evidence from that particular attack and you go backwards. You use that evidence to basically trace back to the attacker, right? Their identity, their IP address, their accounts, and so on and so forth. And eventually, hopefully, you put them behind bars, right? And again, another sort of further afield analogy is if you look at crime in the real world, that's what happens, right? After a crime, crimes are committed. And after a crime, you go and you gather forensics and there's CSI involved and so on and so forth. And eventually you sort of hopefully catch the perpetrator. And what are the benefits? One is you can patch and mitigate the source of the attack, right? If you understand where the attack came from or why it's made possible, then you can go backwards and you can fix the source of that particular vulnerability. And that can basically improve your security moving forward. But also, the fact that there are successful forensic tools means that it actually by itself serves as a deterrent. Because as an attacker, even if you know that you can succeed, that is insufficient. Because you know that after you succeed and compromise the system, you may well leave a trail that even after you get whatever gains that you're trying to get, you can basically be traced down or tracked down and held accountable for the crime. Okay. And that is a very powerful sort of mental deterrent against the crime being perpetrated in the first place. So that's sort of the story behind forensics. And what does forensics look like in a in a machine learning scenario, right? And this is where this upcoming paper is focused on, which is, let's assume that we're talking about data poisoning for now. That's the first paper that we have upcoming at Usenix, and there's other work in the pipeline that looks at broader attacks. But in a sort of fixed setting of a poison attack, right? What do you have? You have, at some early time, at model training time, you have some sort of some set of training data, which includes some malicious data provided by the attacker. Okay, the red triangles in this case. All right. And basically, that training data gets trained into a model, which itself is corrupted, so that at running time, after the model has been deployed, you give it some sort of input, or the attacker gives us some input, and it does something wrong. It misclassifies, right? Some car accident happens, or someone gets misrecognized, something. So the key here then is that this attack happens, and you notice it. Right. So if you don't notice it, then that's problematic. Right. But let's say that, some negative consequence results. Right. There's a car accident. Someone gets authorized that they shouldn't be. And you can trace this back to this model. You can say, okay, this model screwed up. And here's the input that the model basically produced an error on. So there's some tiny little bit of evidence that the model provided a misclassification result. Right, a misclassified result. And that's all this forensics tool needs, right? Is that tiny bit of evidence, okay? And then using that evidence, the goal is to go back and say, in a poison context, what would you like to find? Well, in this poison context, what we like to find is we like to understand which portion of the training data was responsible for training this broken rule into the model, right? Which specific subset of the training data produced this corruption that made this attack possible? Okay, no more, no less, just that particular subset. And if you can find that, if you can go back, then you can do all sorts of things, right? So let's say that perhaps this corrupted data was the result of a data breach, server breach, and someone modified the training data files. Well, then looking at this, you can potentially, identify, looking at, metadata logs for your training data files, for example, you can identify, oh, this looks like this file was, modified by an unauthorized entity on such and such a date. And perhaps you can trace that and correlate that to a server breach, and you can close off the breach or update the server software or whatever it is necessary to close off further breaches. If it came from, a corrupted entity who you pay to label data, for example, some sort of third-party labeling service, and they've been bought off, or they're just really bad at their job, but more likely they're adversarial, then you can basically identify who they are by just looking at logs of who gave you what data sets. Okay, so what I'm pointing out here is that once you identify the malicious data set, you can really take further mitigation steps beyond that to really go to the root of the problem and hopefully fix it and patch it. Okay, so so how do you do this? Well, again, I'm already going on a fair bit of chunk of time in the talk. So, I'll leave sort of super low level details to the Q&A, but I'll give you the high level concept of this, which is that we're going to cluster the training sample set, and we're going to basically iteratively prune out subsets of the training data to show whether a particular subset was involved in the corruption or not. Okay, so the goal at each step iteratively is to remove training clusters that are innocent, that have nothing to do with the corruption, with the error. Okay, and so constantly we're asking this question of like, if I take all the training data that I have available, right, because I am the defender, so the assumption is I have access to the raw training data. Can I prune it, or sorry, can I partition the training data into subsets in such a way that I can, retrain a particular model on a particular subset, and then see whether this misclassification still occurs, right? And to help me do that, I have this little misclassification sample that's part of my forensic evidence, and I can just reuse that same input and retrain models, variants of the models, based on which subsets of training data that we use, okay? And if something has nothing to do with it, training data that looks innocent and benign, then we can basically prune it out and just repeat, okay? So I see there's a question, I'll get to that in a second, right? So the clustering algorithm is basically based on how data impacts the model parameters, okay? And I'll give you some visualizations in a second, but at a conceptual level, you can just think of like, basically where they are in the feature space and what rules they're training into the model. But in the implementation version of that, it's actually even easier. Okay, but I want to get the intuition across first, and so here's a say very overly simplified, two-dimensional space view of the feature set. Okay, and basically what the process is doing is we're taking a look at this training set, and we're saying, okay, this is the entirety of the training set. We're going to make a partitioning cut across the set. So now we have two sets, and we train two versions of the models, and we see which version of the model remains susceptible to this particular misclassification input. Okay, and the version that is clean of that particular misclassification, that training set has nothing to do with this, and you can basically prune that subset of the training set away. Okay, and you should iterate. And you iterate and slowly sort of get to a point where you have identified a immutable subset of the training data that is no longer divisible by some partition scheme into benign versus poison subsamples. Okay, and at that point, over here in this example I have, you're at the right bottom corner where you've identified the specific poison data. Okay, so So why does this work? Intuitively, what's going on? And the answer is basically that if you think about poisoning and why poisoning works, poisoning is trying to overlay a misclassification rule that dominates existing natural features for classification, right? And so in order to overcome natural existing features that are in the training set, it has to be reasonably strong, in particular because when you think about poisoning attacks, you want poison attacks to be reasonably small, right? So you can't say, I'm going to take over 80% of your training data. Well, then everything is easy. You control the entire model, right? But if you control like 5 to 10%, some very small portion of it, then in order for you to convince the model that this rule exists, that particular input has to be so far away from benign inputs as to create a sort of indisputable rule that you're forcing the model to learn, okay, if that makes sense, right? Only by being so significantly far away from benign training data in the feature space can you force the model to extend itself to learn this new rule that you're trying to get it to learn, which is, put on this funny pair of sunglasses and you become Ben or something similar. So that is intuition. And if you look at, here's a really dumbed down, two-dimensional PCA visualization of the training data in the feature space for a bunch of different samples, right? So there's bad nets, which is sort of the original poison training method on CVPR10. There's Trojaning, which is the second paper that came out in that space on VGG face, and the physical backdoors attack on our facial recognition model. This was from the CVPR work just a year ago, right? And in almost all these instances, not almost, but all of these instances, what you see is that the poison data is significantly far away in the feature space from the benign training data, because it has to be, because it is a small portion of the training data that yet somehow has to provide a dominant rule that overrides existing feature classification rules. Okay, so that's sort of hopefully a little bit of intuition for why this is actually occurring. And the fact that you have this natural separation, this significant separation in the feature space, means that it is actually fairly easy to notice that clustering and to partition in that ginormous gap between the benign poison data. Okay, so here's an experimental setup. We can play with little pixel poison triggers. Okay, you've got a bunch of different tasks, different poisoning methods. And we also include natural physical backdoor. So we have access, obviously, to our own training data for facial recognition, which don't use just pixelated triggers, but actually use natural objects in images that are already there. So we integrate that as well. And the key metrics are, of course, precision and recall. Basically, you're asking the system to identify the precise set of poison data. And so precision obviously is, of the set that you identify, did you make any mistakes? And then recall is just, were there any poison samples that you did not include in your answer set, okay? And so those are the results. And of course, the results look great, and that's why it's a paper, but they are surprising in just how high the percentages are, right? 99% basically and above for all of them, with the exception of recall for physical backdoors, okay? And the reason that if you think about what happens when you get a lower recall, right? It actually makes intuitive sense. You get a lower recall when the poisoning data itself is ineffective. And so that makes sense, because in the physical backdoor case, you actually have physical objects that are serving as poor training sets that are having less of an impact on the poison rules. And when that happens, they are in some sense naturally blended in with benign inputs because they're not very good poison samples. And when that happens, the pruning method, the detection method, has a harder job of picking it up. And so sometimes it misses them, and that accounts for the 97% instead of 99% recall rate. Right, so hopefully I answered Karen's question about how do you detect them. Berhanu's question is, can you comment on the possibility of pruning the wrong chunk or missing the right chunk, right? So if I've hopefully given you a sense of the intuition for why this works, And I'll show you some countermeasures for this as well that may help clarify this. But it is very difficult to prune the wrong chunk because the reason behind it is that the gap between the benign and the poison data is so large in the feature space because of the fact that the poison data has a difficult challenge of overriding existing features. So they had to be far away from the feature set so as to actually have a net impact on the model classification itself. Okay. So usually what you iterate through this process, and when you are no longer confident that one of the subsets, so at some point you divide and conquer, and repeat, and at some point you have two portions, and looking at two versions of the model that are created by training them, they either are both corrupted or they're neither corrupted, neither of them are corrupted. That's when you basically stop. That's when you say, okay, I've gotten to the leaf node inside of the tree, and I believe that this entire set is the poison data. Okay, and that's when you terminate the algorithm, as it were. So this method is, as simple as it is, really works well. Okay, let me tell you a little bit more. So we started out by considering only dirty label poison, right? Where basically you say, I can modify my training set input, but I can also modify labels. But obviously, I think many of you are probably well aware of clean label attacks. Clean label poison attacks are where the attacker has no control over the label itself, but can only modify the contents of the data, right? So if for example, I know someone is downloading my Facebook images, so all those downloaded photos of me are going to have the name Ben attached to them. I can't change that. But what I can do is I can change my photos themselves so that perhaps they all fall into the feature space around someone else. And so that it can actually induce a misclassification for that other person. That is sort of like the one sentence version of a clean label attack. So it's interesting that actually, so we tried this out for a clean label attack, and this again works really well. And most notably, the precision is ridiculously high. The recall, again, falls down a little bit relative to precision, mostly because there are samples in the poison set that are just not very effective at actually trying to enact the poison rule. Okay, and these are some of the more recent clean label attacks, both on polytope and witch's brew. Is the cost of training very high in the pruning, since after each pruning step, we need to retrain the model? Yeah, you had to retrain the model, but it turns out the number of iterations that you actually had to go through is actually quite low. And so in most circumstances, we've only had to iterate 3 or 4 times. And so, yeah, there's definitely a training cost. But if you think about like this scenario of an attack has already happened and you're doing forensic analysis after the attack, training time is not necessarily the biggest bottleneck. Because you're not on the critical path. This is not a real-time defense. This is post-attack analysis, and your entire goal is to find a perpetrator. So it's not ridiculous. It's just imagine training small subsets of the model 3 or 4 times. Do you have bounds on the highest percentage of your data that can be corrupted? We have some empirical evidence that's in the paper. I don't think that we have analytical bounds in the typical sense that people use the word bounds. We certainly have no analytical proofs for what is acceptable and within what set of poison we can guarantee attack forensic success. Thank you for that question. So. All right, so here are some countermeasures that we try to push at for our own sake inside the paper. And they all sort of come at it from this concept of, we know why this defense works. We know why this detector works. And that is because, naturally speaking, there's a big old gap between benign and poison data. So what are all the ways that we can destroy that separation and try to confuse the mechanism, okay? So here in part A, you have sort of the benign case, right? So not the benign case, but the normal case, right? So where you have the poison separated within some distance from the benign inputs. And this gap is what our algorithm uses to sort of prune it down and to detect the bad poison subsample. So what are all the things that you can do? Well, you can push poison closer to the benign training data, right? That's example B here. You can inject perturbed benign data in order to fill the gap. to make this less of a clear cluster to try to confuse the clustering algorithm, for example. That's C here with these little purple helper data. So I can give you benign data that has the right label, but just moved around in the feature space to bridge that gap, to look closer and closer to the poison data. You can actually bifurcate the poison data and separate and create clusters in the poison data itself, in the hopes that one of those clusters will actually provide, will make the gap between poison data and benign data closer than the gap between poison data with itself, right? And that can force an early termination in the algorithm and give you misleading results. Or you can basically, provide sort of multiple poison attacks and blend them together and try to confuse the model that way. And the short version of this is that none of these really work. And I'll leave the details for that because I'm rapidly running out of time. But basically, you can look through and what naturally happens, the high level bit, is that as you try to push the poison closer to the benign data in whatever means possible, the poison starts to be ineffective. And so there's a direct trade-off, this sort of fine line the attacker has to walk between allowing for the separation, which means that the forensic tool can potentially detect that subset fairly easily, or making it harder and harder for themselves to actually train the poison behavior into the model. And so the closer that some of these sort of approaches are in terms of looking more and more like benign data, basically what typically happens in those cases is that the poison rule just fails to get learned. And once it's learned, it's usually because of the case that the poison data does have a reasonable gap between it and the benign data, and then they are detected successfully. Okay, so there's more examples in the paper, but I am running out of time. I want to leave some time for questions. So let me try to wrap up. And I, just today, this was just one little snippet of this. But my general take on this is trying to get folks to rethink perhaps some of the goals that we have in adversarial robustness today. And I think that if you look at the existing set of literature and much of the literature and what the target is, it's a very, very narrow definition of what robustness means, right? We're largely speaking, basically looking at back and forth attack and defenses for a single snapshot of a model. And the minute that there is any sort of consistent compromise, we give up and we say, that's it. The attacker has won, and that is the end of the story. And I think we can broaden beyond that threat model in multiple dimensions. And so here are some of the different approaches, right? So one is to say, well, models don't have to be single snapshot. In fact, most companies and places that you talk to today are constantly tuning their models. So what does that mean for robustness, right? When it's not just about a single version of a model that you can compromise, well, that's okay. Maybe I replace that version with a different version with non-transferable robustness, with perturbations that don't transfer to the new version, and boom, I'm okay. And so that perhaps limits the window of vulnerability for some of these attacks. Another version, the second bullet, is what I sort of haven't talked about, which is, perhaps attacks are not binary and immediate, but perhaps partial compromises. So perhaps I can sort of slowly compromise your model in meaningful ways that will escalate and build in the form of stepping stones. And then finally, the sort of the third bullet is what the forensic stuff is trying to address, which is that this sort of definition of attack success is really quite binary and quite limited, which is, okay, I've got some miscompromised results, therefore, you just lost. And really, in a real world scenario, it's much more beyond that. Not only am I trying to just raise the bar and the cost of performing a successful attack, but once attack is successful, I can come back and I can mitigate and I can fix the patch and I can apply forensics to trace back and identify the attacker. So yeah, that will be the end of my talk, and I still have a few minutes for questions, I hope. Thanks.
Yeah, thanks a lot, Ben, for such an amazing talk. So yeah, let's thank our speaker before we move on to questions.
Thanks. It's always funny to do that over Zoom.
Yeah.
So yeah.
I think there are some questions in the chat which I think we kind of like missed during the talk. So I think like for the latter half of the talk, there's a question from Saeed on does the approach have a way to distinguish?
Right. Oh, this is very good. Yes. Does your approach have a way of distinguishing between benign error points and backdoor instances during inference? Right. So there is a question of, this gets at a sort of an earlier question, which is, if a sample comes across during inference time and is misclassified, what do you assume about it? Do you already assume that we know that it's an actual poison attack, or do we allow for the possibility that this is a normal, natural misclassification example just because a particular corner of the feature space was not as well trained as we like it to be? That's a great question. So that comes at the question really at the topic of attack identification, right? Which in a way, throughout the talk that I've talked today about, I've basically assumed that you already know it's a poison attack. So that's, of course, not really a given, right? In a real setting, you don't exactly know, and you have to figure that out. What is interesting, so I don't have a good answer to this, except I will say that in many cases, in a practical setting, you can figure out, in a forensic setting, you can figure out what the trigger is, and you can repeat it to confirm that it is an actual backdoored instance and not just a random sort of slightly vague input that's causing benign misclassification. But that's not a really good answer. What I can also offer is that, interestingly enough, this particular technique is that I talked about today in terms of forensics is reasonably good enough that you can actually use it to go backwards and to identify whether something is a natural misclassification or it's a backdoor instance. Does that make sense? So if you're at all confused about whether misclassification is natural or backdoor, you can actually just apply this technique and see what comes out of it. And if it comes out and gives you a very specific subset that says, this is the subset of training data responsible for the backdoor, then you know it's actually backdoor. If it's a natural misclassification in all of our testing, because we actually did test this, what actually happens is that almost immediately the model, the forensic tool basically just stops and just says, nope, there's no natural partition here, so we give up and we think this is a natural misclassification. So I think that hopefully is a reasonable answer. Okay, so Tan-Hao's question, are you retraining the model after each pruning? Yes. Yes, that is basically what we're doing. Can you just identify the points data via influence function techniques? So no, the short answer is no, because so I can't say for sure that function doesn't work. But what I can say is that in our experiences, not particularly focused on this particular paper, but in our other experiences related to the space, what we found is that anything that is dependent more on sort of influence inside the model, activation patterns, activation clustering, activation values, those type of functions have been shown to be reasonably brittle, particularly when the backdoor inputs are natural and not digitally enhanced or inserted. And that's one of the things that we took away from the physical backdoor paper at CVPR last year that we had, was that most of the defenses that failed because of similar kind of assumptions about influence and activation patterns in the neural model. So I can't say, I don't recall whether we tested that particular technique explicitly. So I can't answer that specific question, but our general take is that anything that relies on activation patterns and influence is a bit more fragile than we would like. And so we just go with the more dumb, perhaps higher, more costly approach, but less prone to assumptions that may or may not hold true. Is the cost of training very high? I think from Akash that I tried to answer during the talk. Do I have bounds? Yeah. Do you see this technique from Trung Yang? Do you see this techniques being adaptable outside a classifier model? For example, transformers training on sequence of data. That would be very, sorry, Kieran has a question that I didn't answer yet. Do I see Troyang's question? I don't know. I don't understand enough about transformers to really conjecture on that. I don't know. I think the architecture behind transformers is complex enough that some of the assumptions that we make about poison versus benign data and the separation can fall apart in that space. So I wouldn't conjecture on that. I had to do some tests and dig further to just understand whether some of our assumptions still hold true. So we're not sure. We don't know. Kieran's question: in what space is the difference between clean data and poison data? Yeah, it's you know, the PCA is just a oversimple visualization that we used. But in most versions of what you could define to be some sort of Euclidean lower dimensional space that you can reason about, that seems to hold. So I could imagine, I'm sure, you know, higher dimensional spaces that you try to characterize feature distance by, and I believe that those would hold. So it's not some sort of artifact introduced by a really low dimensional space like PCA or low dimensional dimension reduction mechanism. We believe it's pretty fundamental. It is intuitive that it matches with what we believe poison training data has to do in order to get their job done, right? Which is that if you think about, if you have poison data which is adjacent in the feature space by in some dimension to next to benign data, then it will have just a tougher job of convincing the model to extend its classification rules in a discrete way to account for it. So you would imagine that intuitively you need to be separate in the feature space enough that the model has to behave differently to account for it, not just, you know, extend the classification boundary by a small quantitative amount. Okay, I think those are all the questions in chat. Anyone else have other questions?
Yeah, I think this was like super ideal time, like in terms of length. Like we ended like precisely at like in 1 hour. Yeah, since there aren't like any more questions, we can thank our speaker again for such an like amazing and like super engaging talk. Yep.
Thanks, everyone.
So again, yeah, thanks, man, for like the great talk. And yeah, again, on the logistic front to everyone, the seminar next talk is scheduled next Tuesday, again at 1 p.m. ET. And I think the guest speaker will be Professor Kamalika Chaudhary. So again, super excited to see you all there. Thanks.
Thanks, everybody.
Bye-bye.